Okay, I think we are ready to roll. We still have a couple of seconds left, right? Yeah, I think it is midday now. So, do you recall what I did in my last class? Yes, do you recall what I started? I started integral surface. I started integral surface. Okay? Yes or no?
Yes, sir.
Yes. Okay, fine. So let us get back to integral surface again. So integral surface, it appeared only because we were dealing with something like this is equal to 0. If you recall, it has some association with that differential equation, right? And what we did, we considered a vector field. We considered a vector field, of course. It is non-vanishing, so that means at least one of the components P, Q or R, it is non-zero, right? In R3, and of course we define that in a region omega in R3, okay? And then associated with this vector field, what we had a function, u of x, y, z, a function of 3 variables, again defined in that region omega. And then what we did, if this function satisfies this equation, so basically grad u dot v bar, if this is equal to 0, we called this function to be what? This function to be? Yes? This function to be what? If this function satisfies this equation, u is called what? First integral. First integral. You guys have forgotten everything in a week. It is called first integral. Okay? It is called a first integral. Okay? So now, what is the definition of integral surface? So suppose I am considering a surface S. This is a surface in some, say, in some region omega in R3, right? And we say that this surface is an integral surface of the vector field V, right? If what? It is the level surface of a first integral. It is a level surface of a first integral. What? First integral of V, right? So that means suppose I define this surface S by this is equal to C, where C is a constant, So then this is going to be a level surface. This is going to be an integral surface corresponding to the vector V bar if that is satisfied. So that means that is satisfied. Q Uy plus R Uj, this is equal to 0 if this is satisfied. Is it okay? Fine. So as somebody pointed out, so that means what is going to happen on this surface, say suppose this is the surface S. So at each point, what is going to happen? This vector field V, right? So if you consider, suppose V is given by PQR. Of course, PQR themselves are functions of X, Y, and Z. So then, suppose you consider a particular point here, say at each point of this surface, say suppose you consider a vector defined by this formula, so then that vector is going to be tangent to that surface. So tangent to the surface, so that means if that particular point you draw a tangent plan, then that vector V is going to lie on the tangent plane. Is it clear? Right? The definition of integral surface. Is definition of an integral surface clear?
Yes, sir.
Right.
Yes, sir.
Okay. So now there is one thing. We are considering this integral surface. We also know about integral curve because this is going to be repeatedly come in our discussion later on. Integral curve. You already know what is an integral curve, right? So if you define a curve in say again in some reason omega in R3 in such a way that right at each point of the curve this vector field defined by v, right? V is a tangent. So then we say that that curve C is an integral curve corresponding to the vector field V, right? So now, one thing I want to be very conscious about is that, say, suppose I have a curve here C, I have a curve here C, okay? Remember, this C, suppose it is lying on this surface S, which is an integral surface of the vector V, then like say any curve if you draw, it may seem to you that any curve if you draw there, it is going to be an integral curve. No. See, weaving a tangent vector on the surface merely indicates that it is going to lie on the tangent plane drawn at that particular point. Okay, it is not going to give you any particular direction of the tangent vector. Remember that. Are you getting my point? Are you getting my point? Say, suppose this curve is lying here. I am taking a particular point here, right? So at that point being a point on the integral surface, I must be able to draw the vector v bar as a tangent, right? But that doesn't mean that it is that this say suppose this is v bar at that particular point. That doesn't mean that this v bar has to be along the direction of the curve at that point. Are you getting my point? Because this concept is going to be important later on. Because you may be thinking that, oh my god, any curve you draw over there in the integral surface, it is going to be an integral curve. No. Is it clear now?
Yes, sir.
Right?
Yes.
Okay, fine. Now, again say, if it has to be an integral curve, so obviously that is going to come from the associated differential equation that is going to come from this associated differential equation. So then what you do, you simply solve this equation, and then what you do, you get two two first integrals, right? And then you take this from the two parameter family of surfaces. Like say you are going to have two surfaces. Again, what is going to happen? Those two surfaces coming from those two first integrals, if they are functionally independent, then definitely we will be able to get an integral curve out of those first integrals, right? Okay, this is just some kind of revision I want to do before I move ahead. So now you may be asking me why this concept of integral surface is so important. Why this concept of integral surface is so important? Because what we are trying to do, we are trying to construct an integral curve on which we are trying to construct an integral surface on which a particular curve lies. Okay, that curve may be an integral curve, that curve may not be an integral curve. Okay, fine. So that is what we are going to do. So before that, maybe we can take two small examples. Say suppose your V is XYZ. V is XYZ. Okay. So now, if I want to find out the corresponding associated differential equation, so it is going to be something like this. It is going to be something like this, right? Is it okay? Fine. So then earlier what we did, in order to find out the integral curve, we just consider two surfaces, right, coming out of two first integrals of V. Is it okay? But here what it is, let's say if I simply plug in those components, so from here I can simply get what? Your x by y. So u1 x y z equal to x by y as one of the first integrals, isn't it?
Yes, sir.
Right? So then you can see that. I mean, if you consider this level surface, so suppose I call it say S, this level surface S. So it is simply going to be some plane passing through the origin, right? Which will be given by x equal to c1y. Is it okay? Fine. It is going to be
Yes, sir.
right. It is simply going to be some planes. Okay. Fine. So this is going to be an integral surface. This is going to be an integral surface. So similarly, say integral surface, right say here you simply need one surface. Okay. Fine. So similarly, say suppose I take this one 0. I take this one. So then you know that from here I can get something like x square plus y square equal to c, which is nothing but what? A circular cylinder, right? A circular cylinder,
Yes, sir.
right? On the xy z space, right? So this is also going to be an integral surface corresponding to this vector field. Is it okay? Fine. So now what we are going to do, we are going to find out an integral surface, which we are going to show that it is nothing but the union of integral curves. Okay, it is nothing but the union of integral curves. Okay, so what we are going to do, we are going to develop some theory. Okay, we are going to develop some theory, as I have told you, because it is going to come out of the integral curve. So that is why I will always have to associate this equation, this. Okay, so let us try to, prove one theorem. The theorem has two parts. So what I am going to do, rather than confusing you with both the parts at one go, I will try to prove them part by part. Okay, I'll try to prove them part by part. Okay, fine. So maybe let me method of constructing and integral surface. Okay, and again I have taken it from How. So you please go through that theorem. Okay, so let me and again just before I go ahead, see, I told you about integral surface, right? I told you about integral surface. Now, what happens? You know that integral surface, it comes from the first integrals, right? So simply what you have to do, you have to equate the function for which came as a first integral, you have to equate it to some constant. Is it okay? Fine. So basically, if this is a first integral of the vector v, right? So then what must happen? This is nothing but the solution of this differential equation, right? Okay, right? And simply by equating these to some constant, we get an integral surface, right? So that is why the integral surface, it is sometimes also called solution surface. Huh? So solution surface. So in this theorem, I am simply going to write this. No? I am simply going to write this solution surface. Okay. Okay. So if S is a solution surface of zero, say in omega, we want to say R3, then for every point in omega, let's bring it to omega. Again, say the integral curve, they are also called the solution curve. Okay, the solution curve of this one. So basically, I am associating a vector field. This, let me call it 2. This passing through that point lie entirely on S in this. Okay, say could you please go through this theorem once again, because I mean geometrically you have to understand it. So what it is saying, say remember, I am talking about an integral surface or a solution surface, right? And obviously you know that the solution surface, it is going to be given by something like u of x comma y comma z equal to c1, right? So then what it is saying is that I am considering a curve passing through, say suppose a particular point on that surface, fine? And then if that curve is an integral curve corresponding to a vector field V whose components are P, Q, R, of course, at least one of them has to be non-zero. So then what happens? That curve must lie entirely on that surface. Are you getting my point? So maybe what I am going to do, I am going to what? Draw it, okay, so that you can visualize it. So simply I am going to call this 1 and this as 2. Okay, remember please these two equations. Okay, fine. This is part A. Part B is still to come, but let us not rush it. Okay. So what it is telling you, say suppose this is S. This is an integral surface, okay, corresponding to that associated system. And suppose I'm considering, suppose this point is say x0, y0, z0. X0, y0, z0. Okay. So now, obviously, through this point x0, y0, z0, I can draw infinite number of curves. Is it okay with everybody? Fine?
Yes.
What the theorem says is that if I have an integral curve of the associated system passing through this point, that curve, say suppose the surface was something like this. So that curve it has to entirely lie on S. Basically, what it is telling is that this curve cannot be something like this. I mean, passing through this. Are you getting my point? The geometric meaning of the theorem. Are you getting it?
Yes.
Right? So this is what it is saying. If this is an integral curve, it must lie on the integral surface. Okay? So that is what we are going to do. Okay, let it be there. So let the integral surface as the given by, say, this equation x, y, z. So I write. So maybe I'm going to write it as A. In your book, they have used C because that C and the curve C, you may get confused. Okay, so let me call it capital A. U x y z equal to A, right? And uh, and let CB, let CB and integrate integral curve of say 2. 2 you know, it is nothing but dx by p equal to dy by q equal to dy by j. Okay, fine. Okay, fine. So let and maybe I will simply write and let's see the integral curve of 2 maybe which is parameterized by say this x equal to xt, y equal to yt and z equal to zt for some, of course, small t belonging to some interval I, okay, and all these they are C1 function defined in I. Fine, so far so good. Okay. So these are the two information. So now I'll come to a fixed point. Okay. Let integral curve of. Okay. Should I? Okay. Let C pass through some point x naught, y naught, z naught. This which lies lying on S. Is it okay? Fine. So far so good.
Yes.
Right? See, now what is happening? X naught, y naught, z naught. It is a point lying on the curve C, right? And C has been parameterized by xt, yt, zt, where t lies in that interval, right? So therefore, what we must have? There exists some t naught belonging to I, right? Such that your x naught equal to xt naught, your y naught equal to yt naught, and z naught equal to zt naught. Is it okay with everybody? Fine? Is it okay?
Yes.
Thank you. You guys have become more and more silent. Okay, fine. So now see what is happening. My situation is something like this. My situation is something like this. Let's suppose this is x naught, y naught, and suppose like this is my Okay, so then I mean I can this. Okay, and what is happening? Suppose this is my C. This is C. This is surface S. This is my C. So I'm going to do something like this. Okay. So now what is happening? This point, it is lying on the surface S. It is on the curve C as well, which is parameterized by this, right? So then what we must have, like your then u x naught y naught z naught, u at x naught y naught z naught. Okay, so this is simply u x t naught y t naught and z t naught, isn't it? Right? This is straightforward.
Yes, sir.
Right? And again, you know that if any point lies on the surface S, that point must satisfy the equation A. That means u x y z equal to A, small a, right? So this is equal to A. Is it okay with everybody?
Yes.
Fine?
Yes, sir.
Okay. See, remember, we shouldn't deviate away from what we are planning to do. We are planning to prove that. The curve C entirely lies on S. Is it okay? Fine. So now let us see what happens here. Let us see what happens du dt. Right? So what we want to do, we want to check the variation of u in the interval I. You should think like that. Is it okay? Variation of u for all t lying in that interval I. We should think like that. Okay. So then you know that u is a function of x, y, and z, and x, y, z themselves have been parameterized by your what? Parameterized by the single parameter t, right? So this is simply what? Del u del x dx dt plus del u del y dy dt plus del u del z dz dt. Is it okay? Fine.
Yes.
So now again what is happening? This this variable t, it lies what? This variable t over the interval I defines the curve C, isn't it? And that curve C was nothing but an integral curve. So from here, what I'm going to get? Pux plus uy plus r uj, isn't it? Right? Is it okay? Fine.
Yes, sir.
And again, what is our original differential equation? What is our original differential equation? From the definition of integral curve, this u, it satisfies this equal to 0, isn't it? Only from there the definition of integral surface came from, right? Is it okay? So u being a first integral of v, from here I get this to be equal to 0, right? So that means what we must have, u x y z, this is equal to constant. This is equal to constant for all t belonging to I. Right? So far so good.
Yes, sir.
Yes.
Yes, sir.
But we have already proved that for a fixed t naught lying on that interval I, what I get, u is equal to a, isn't it? Right?
Yes, sir.
For one t, which is t naught, I have already found out that constant is A, right? Isn't it? So for all I, this being a constant, it must be the same. Are you getting my point?
Yes.
Right? So therefore this must be equal to A, right? This must be equal to A. Now if you see that this is u x y z equal to A for the entire curve C, so that means that curve C must lie on the surface S because it is satisfying the equation of the surface. Is it okay?
Yes, sir.
Right? Okay. And if it is a bit difficult to understand, please go through it once again. I mean, this is explained in Thobo, but I'm not sure they're going to explain it. I mean, extensively. So this is it. Okay. The second part of the theorem. Yes. Yes.
Initially, the curve was integral curve corresponding to which vector field?
V, because I have already told you that this corresponds to dx by p, dy equal to q, dz equal to r. And of course, when I am considering this as an integral surface, again this was corresponding to that vector field v.
Then sir, why dUdt, that is ux dx dt plus cy dy dt plus uz dz dt, that is equals to 0.
That is equal to
0, the last step.
haha.
dUdt equals
Yeah,
to
yeah.
ux dx dt plus
Ha,
cy dy dt.
ha.
That is equals to 0 by.
No. See. Just a minute. I am. That is equal to 0. Okay, that is equal to 0. It is coming from any u, right? Any u is going to satisfy that. Any u is going to satisfy that. Isn't it? That has come from the equation. That has come from the equation. See, from the definition of integral surface itself, I am going to say that this is an integral surface. This is an integral surface corresponding to the vector v, right? If this happens, if this is a first integral of this, right? So this being the first integral, that came from there. That came from there. Because see, I have been given an integral curve, right? But I still don't know whether that curve is going to lie on the surface or not. As I have told you, that any curve passing through this, it can be something like this, isn't it? So we have proved that if this curve is an integral curve, it must lie on the surface itself. Is it okay? Fine?
Yes, sir.
Okay. So now the second part, what it will tell you is that suppose you have considered a surface, and through each point lying on the surface, you draw an integral curve. Say, you draw an integral curve, and from there, I am going to prove that. Under certain circumstances, that just a minute. See. Suppose I am considering a surface. I am considering a surface, but I still don't know. I don't know where this function comes from. What is the property of this function? Okay. So the part B, what it is going to tell you is that conversely, if u is a C1 function, of course it is defined in that region omega belonging to R3, C1 function, u is a C1 function, of course, in omega, and the solution curve of 2. 2 is nothing but dx by p equal to dy by q equal to dy by j. So basically, this is nothing but an integral curve corresponding to the vector v with components p, q, and r. Passing and the solution curve of 2 passing through each point x, y naught, z naught belonging to omega lie on the level surface of u, passing through that point, then u is a solution of 1. 1 is nothing but pux plus quy plus rdz in. Okay, I'll just geometrically explain it. Okay, just passing through. Okay, fine. Now, suppose I have considered a point here. I have considered a point in omega, right? And then, what it is saying that I have a, suppose I have a curve C, right? And then what happens? You may get a level surface defined by d is equal to constant passing through this point. Okay. So now what the theorem is saying that if this level surface contains this integral curve, then this function u must be a solution of pux plus quy plus r uj equal to 0. Is it clear to everybody?
Yes, sir.
How many, like now one thing, say, you shouldn't think that we are going to have only a single surface out of this passing through that point. We can have infinite number of surfaces passing through that point. Okay? Because what is going to happen for different values, we are going to get different different surfaces, isn't it? Is it okay with everybody? But see, I am not talking about the same integral curve lying on those infinite number of curves. No, it is not going to be like that. So maybe again, I am going to tell you about the construction just after proving this. So then it is going to be more clear to you. Okay. So basically, what it is saying is that you take a particular point, right? Through that point, you have an integral curve, right? And then you consider a level surface. On which that integral curve lies. So then the function for that level surface, it is a solution of the given differential equation pux plus qey plus r uj equal to 0. I think you can easily prove it. Can you prove it? Can you prove it? See, basically I have to prove that this, I have to prove this, isn't it? For this function. Is it okay with everybody? Yes? So from the given information, can you do this? I think that is pretty straightforward. If have you thought about it, how you are going to do that? Yes? Okay, fine. I am giving you a hint. Okay. See, suppose this is my u x y z equal to constancy. Fine. And what property I have? Say if you take any point here, you draw an integral curve passing through that point. It is again going to lie on that surface, right? And then you have to prove that what you want to prove, like this u is a solution of this differential equation. So now what is going to happen? Say suppose this is an integral curve. So that means at each point v is going to be a tangent, isn't it? Are you getting my point?
Yes.
Right?
Yes.
So consider a point here, x naught, y naught, z naught. X naught, y naught, z naught. So then what is going to happen? At this point, if you draw a tangent plan, so then this v is going to lie on the tangent plan, isn't it? Yes?
Yes.
Yes.
So that means grade u at that point x naught, y naught, z naught is going to be a normal, right? So that means grade u dot v, that is going to give you 0. Is it okay? And since I have been giving that in this information in the theory statement part, I have been giving that it is going to happen for at each point that happens. At each point that happens. Right? So what? That is why this is going to be satisfied for all xyz in omega. Is it okay? You please have a look,
Yes.
right? You please have a look at this statement. This statement itself is giving you the proof. It is pretty straightforward. Okay? So then I am not going to write it down. You simply, systematically write it down. Yourself. Okay? Fine. So now here comes the most interesting part. So now I think the next part you are going to appreciate this. No? There's still some confusing information. Okay. So construction of an integral surface of a vector v say through given curve say C. In some reason omega in R. C in some reason say omega. So now I think you would appreciate all this stuff, the previous theorem. You will appreciate the previous theorem. So previous theorem, it gives you a hint that, like say, you can construct an integral surface by combining all those integral curves. Okay? So how to go about this? Okay, fine. Suppose I suppose I consider a curve. I consider a curve in omega. Okay, and I want to construct an integral surface in such a way that this curve is always going to lie on that surface. Is it clear? Is it clear?
Yes, sir.
Right? So here there may be two cases. So case one, phi is not tangent at any point of C. Phi is not a tangent at any point of C. So then, can you think? I mean, how we are going to find out the integral surface? Yes. Just idea. I'm not proving any. I mean, like say, I'm not developing any theory. I'm not giving you any statement or theorem, and I'm proving it. I'm just telling you to give me an idea. Okay, fine. How?
So we can choose another vector which is parallel to this vector P and is equal tangent to C.
Then what is going to happen? The parallel to this vector. How can see vector? I mean, you can have translation by displacing it. By displacing it, again you can make it tangent to that. If I take a parallel vector, I have, say, suppose V is tangent here. So by shifting V will be tangent there also. I can do something like that. Okay. So here, let me tell you what we are going to do. Say I choose at each point, what I am going to do through this point. Suppose I draw an integral curve. Say suppose. So then what is going to happen? At each point lying on the curve C, if I draw an integral curve, so that means V is going to be tangent to each of those integral curves, isn't it? Is it okay? For the time being, I mean this construction, whatever I have done for these 3 points, is it okay with everybody?
Yes, sir.
Right?
Yes, sir.
So now I can repeat it for each point, right? So then it is going to generate it is going to generate a surface. It is going to generate a surface like this, isn't it? And that surface is going to be nothing but the integral surface. Now it looks pretty straightforward and easy, but another information. Remember, through a particular point lying on the curve C, we will be able to draw only one integral curve. Why? Why? It is going to come from this. I have dx dt equal to p, right? P x y j. Similarly, dy dt equal to q x y j, and your dz dt equal to r x y j. Okay. So what we are doing here? These three. I have three equations here. First order equations, right? And I have an initial condition. I have got an initial condition somewhere here, right? Say, suppose I am parametrizing this curve, which say this, right? So then I can always find an initial condition. corresponding to some T naught belonging to some interval I, right? And suppose this point is nothing but that initial condition, isn't it? Is it okay? Fine. So that means we have an initial value problem. We have an initial value problem, right? And we had assumed, what we had assumed that PQR, they're not only, they are, simultaneously non-vanishing, but what we also assume that they are C1, isn't it? PQR, they are also C1 in I with respect, sorry, they are, that is fine, because if I assume x, y, z to be C1, C1 in I, so definitely what is going to happen? The first order derivative of PQR with respect to what? With respect to, if you recall that initial value problem, what was that? Okay. Isn't it? So PQR, Px is continuous, Qy is continuous, Rj is continuous. Are you getting my point? Basically, what I am trying to tell you is that this system has a unique solution corresponding to an initial value. That is what I am saying. Okay. So then what is going to happen? Through each point you can consider it as the initial point, right? So the curve passing through each of those points, they must be unique curves, isn't it? Right? So you take the union of all those integral curves passing through each of these points, and that is going to give you what? That is going to give you the integral surface. Why? Why integral surface? Integral surface, what is the definition of integral surface? Corresponding to that vector V, V must be a tangent at each point, isn't it?
Yes, sir.
So that means you take this. So then that condition is satisfied at all the points, isn't it? You take any other point, and then at each point, right? Isn't it? So it is going to embed the whole surface, isn't it? At each point you are going to get what? V as a tangent. Are you getting my point? See, I am telling you that if you take the union of all these integral curves passing through each point of the curve C, it is going to give me an integral surface. Okay, fine. Why I am emphasizing on V being tangent at each point? Because I know that it is going to give me a surface. But what is the guarantee that that surface is an integral surface? In order for that surface to become an integral surface, I want at each point the vector V be tangent, right? And that is going to come from the fact that each of those curves passing through each of the points of the curve C, they were nothing but integral curves of the vector. So that is why at each point of that particular curve, each point of this particular curve, I am going to get V as a tangent. So this kind of curve is going to embed the whole surface, isn't it? Right? So that is why at each point I am going to get the vector V as a tangent. Now is it clear? I cannot repeat it more than that.
So
Yeah.
pictorial construction is not clear. This is we taking this pictorial construction, how you are constructing.
See, I am firstly what I am assuming. This is case one. I am assuming that I have a curve. I have a curve. Okay, I have a curve lying in your omega. Fine. So then I am also assuming that this curve is not an integral curve. So that means at each point of this curve, v is not tangent. Okay. So then what I have done, at each point I have drawn an integral curve. I have drawn an integral curve passing through that. So then what I am getting, because this integral curve, it came out from this system of equations, right? So that is why that curve, any integral curve passing through a particular point lying on this curve C must be unique, right? So all these unique curves, they are going to embed to generate a surface, and now I am claiming that that surface must be an integral surface corresponding to V, and that is pretty obvious, although it is still not obvious to some of you. That is pretty obvious because the very definition of integral curve itself tells you that at each point V is a tangent. Is it clear now?
Yes, sir.
Okay, fine. So now what I'm going to do, yeah, can you tell me what will be case 2? What will be case 2? What is going to happen to the given curve? Yes?
If V is tangent to at least at one point.
No, all points. All points. It is an integral curve. It is an integral curve. Okay. I'm going to assume that you're now. Okay. Please don't blame me that I'm not doing from this side. I'll tell you, just because I have already told you something from this direction, so that is why what now I am doing. I am now assuming that my given curve C is an integral curve. So that means at each point C, your V is going to be a tangent. Okay, fine. So now what is going to happen? Like suppose you take a point here on the curve C, and through that, suppose you want to draw an integral curve corresponding to V. Similarly, you take another point here, again you want to draw an integral curve corresponding to the vector V. What are you going to come up with? Say, for the time being, forget about the existence of the curve C. Okay, suppose I only know about the set of points which is constituting the curve C. Fine? Okay. Now, suppose I am trying to draw an integral curve through each of those points. What I am going to get? I'm still not sure whether you are getting at what I'm trying to get at. Okay, fine. Say, suppose I'm taking a set of points, okay, and by joining those points, say, suppose I can draw a curve. So now, suppose those points have been derived from an integral curve corresponding to V, say. Okay, fine. So then now suppose through each of these points I am trying to create an integral curve corresponding to V. So then what is going to happen to those curves? Can you tell me that? Yes? Those curves are going to overlap because through a particular point, the integral curve drawn is going to be always what? Always unique, isn't it? Are you getting my point? Am I still on here? Yes?
Yes, sir.
Now, are you guys getting my point or not? Right?
Yes, sir.
Because see here, I cannot do whatever I have done earlier. So suppose at each point, I want to draw an integral curve, right? Through each point. So then what is going to happen? I am going to end up with the same curve. That is the point. But now, what I am going to do, I am going to take an integral curve of V which intersect this particular curve C. Okay, suppose I call that curve as C prime. Okay, so now I am claiming that if I repeat the same system, the same process that I did for case 1 for this curve C, it is going to generate an integral surface. Agree or disagree? Yes? What I have done, I have chosen an integral curve of the vector V which intersects the given curve C at some point. Okay, so now on this curve C, what I am going to do? Sorry, on this curve C prime, at each point, what I am going to do? Just a minute. Not at each point. Just a minute. Just a minute. I think I'm confusing it. No. Sorry. Because I sorry. Let me repeat it again. Okay, sorry. See, I have already been given a curve C. Which is an integral curve, right? And then I told you that if I take all the points here, again I want to draw some integral curve passing through that, I am again going to end up with the same curve. Up to this it is fine, okay? So now, what I am going to do, I am going to draw one curve C prime, which intersects the given curve C in such a way that this curve C prime here, the vector V is nowhere tangent. Nowhere at all the points in this curve, I mean the vector V curve is a tangent. Is it okay now? That means I am not going to get at each point here. The tangents in such a way that the direction of those tangents are parallel to V curve. Is it okay? Now is it okay? Yes?
Yes, sir.
Right? So now I am claiming that I am going to repeat the same process. As in case 1. So then what I am going to do, at each point I am going to draw an integral curve. And that is going to give me the union of all those integral curves. It is going to give me the required integral surface. Now is it clear? Yes?
Yes.
Right? But there is still one thing. What is the guarantee? That this curve C, this original curve C, is going to lie on the integral surface generated through the newly constructed curve C prime? Can you tell me why this original curve C, which is an integral curve, it must lie on the surface generated by the curve C prime at each point of which V was nowhere tangent. Yes, can you give me the explanation?
So if we try to find integral curve at the point of intersection, I think that will be C only.
Yes, because that is unique.
Yes.
Right? Because that is unique. Is everybody getting it now? Yes? Is everybody right?
Yes.
The uniqueness is going to guarantee that at the point of intersection, whatever integral curve you are going to draw, it is simply going to give you the original curve C. Right? So that means the original curve C is always going to lie there. So now, I'm sorry that I got confused there, because again, I call this as integral curve. No, this is a curve where V is nowhere tangent. So now, can you tell me that in this way, how many integral surface can you generate? In this way, the way I have done it here. In this particular case. Yes? See, I may have a curve like this. I may have a curve like this, isn't it? Say, suppose this is my curve, C double prime. Because I am considering curve on space, remember. Right? Isn't it? By drawing different curves which intersect the original curve at a point, I can generate different integral surfaces, isn't it? By repeating the same procedure. Right?
Yes, sir.
So in that way, we will be able to generate infinite number of integral surfaces. Okay? But what will be the common with all those surfaces? That this is going to, the original curve is going to lie on that particular, on those surfaces. Okay? Fine. So, are you convinced or not? Is everybody convinced that, okay, like given a curve in space, we would always be able to generate an integral surface on which that curve is going to lie. In fact, I would appreciate a no more than yes now. I'd be happy if I haven't been able to convince you completely. Can you tell me why? Can you tell me why? Why I'm telling you this? Yes? Can you tell me why? Because say, I have told you only about a procedure, right? I haven't developed any theorem which is concretely going to prove that whatever procedure I told you about, that is going to work. Are you getting my point now? Yes? Right? So,
Yes.
what I'm going to do now, I'm going to develop those theorems which are definitely guarantee you an integral surface on which a particular curve is going to lie. That is what I'm going to do. Okay. So for this formulation of theories, maybe I will just be able to state one theorem. Okay. So what I'm going to do, say here, firstly what I'm going to consider, I'm going to consider a curve. I'm going to consider a curve. Okay. And this curve, I'm going to consider that it is passing through a point, this. Okay. And what I'm going to assume that this curve C, it has the parameterization given by this. Given by, please remember here you may be thinking that parameterization given by this, okay? Where your this x0, y0, z0, obviously they are this C1 in I, okay? C1 in I, of course. I mean this T before that your T belongs to some interval this. Huh? I'm always going to assume this parameterization. Okay, fine. And again, another thing I'm going to assume that this derivative of these three functions, okay, so they don't vanish in I. They don't vanish in I. Okay, fine. They don't vanish in I. Do I need all of them non-vanishing in I or what? Hmm? At least one of them not vanishing. Okay, at least, and let us assume that at least one of these three are non-vanishing in I, because that is going to guarantee me a tangent vector. Is it okay with everybody? Fine? Okay. So then again we are going to assume that this point x0, y0, z0, it corresponds to the fixed point T0 belonging to I. Okay, so this is going to be common to, in fact, I am going to prove two theorems. Okay, so these facts are going to be common to both the theorems. Okay, now another interesting thing you must have noticed here is that, say, I have defined these functions here through which I have parameterized the vector C. I have defined it as x0, y0, z0. Do you have any idea why I am doing like this? Why I am doing like this? Yes? Just a wild idea will also do. See, this curve C, sometimes it is also going to be called an initial curve. Okay, it is also going to be called an initial curve. So that is why these symbols are being used. Okay, fine. So now this theorem, you will see that this theorem is straightforwardly whatever we have done in case 1. So suppose that this vector V given by PQR is not tangent to C, say at x0, y0, z0. See, then in some neighborhood, let me call it omega naught of x0, y0, z0, there exists a unique integral surface of V, meaning integral surface of V, of course, containing let me see here, okay. Are you getting my point? Why it is saying containing that part of C? Yes? See, here, what is being given? We have been given a vector field V, right? We have been given a vector field V whose components are P, Q, and R. Again, we are given a curve C in some region omega in R3 such that it passes through x0, y0, z0, and of course, I mean the curve C has been parameterized as the way I have done it before. Okay. Now, what it is telling you is that this vector V is not tangent at any point of the curve C, right? Then it says that what it says that you consider a very small neighborhood of this point, small neighborhood of this point. It may be some open set in R3 containing this point, right? We are calling it omega naught. So it says that in some neighborhood, that is here in omega naught, there exists a unique integral surface of V. Again, because I am considering only Jiten in omega naught, so that is why the entire part of C may not lie in omega naught, isn't it? Sometimes it may be, because you never know, because your original omega may be R3 itself, isn't it? Then the whole entire curve may lie in that particular neighborhood. So that is why, because we are only considering a neighborhood of this point, so that is they are saying that part of C in omega. Is it clear to everybody? Yes? Is it clear to everybody?
Yes.
Right? So basically what it is telling you that it is telling you about a locally satisfying theorem. Okay, but it doesn't mean that you cannot extend it to the whole, extend it to the entire, omega. Okay, how much time do I have? So maybe this theorem and the next theorem I'm going to prove tomorrow. And before that, let me tell you is that what I have been doing, I have been following this Jackman and Taubo, and so far till now, what I have done, I have dealt with something like this. I have dealt with this. Okay, see, I'm dealing with equation like this, but I still haven't categorized this equation. I don't know whether you have noticed it or not. And in your syllabus, they are talking about quasi-linear, linear, all those stuff. But so far, I haven't talked anything about it. See, here in this particular case, it is quasi-linear. It is quasi or quasi-linear. Okay. So now, what is going to happen? All the theorems that I'm going to, so I have been considering so far in this PDE course, like say they have been developed for equations like this, which is a quasi-linear equation. Later on, we are going to see that if we understand all the concepts, clearly, it is similar to, whatever is going to happen to linear equations as well, because linear is much easier than quasi-linear, isn't it? So later on, what we are going to do, we are going to consider z as a function of these two variables x and y, right? And what we are going to do, we are simply going to replace ux and uy by zx and zy, and of course uz. Then it is going to be what? If I consider u xyz to be say z minus f of xy, right? So uz is simply going to be 1 or minus 1. Is it okay with everybody? Right?
Yes.
Right? Accordingly, how you choose it. You may choose it as fxy minus z. So then, what happens if it is minus 1? Then it is simply going to be r. So basically, I am going to deal with pzx plus qzy equal to r. Because you already know the tougher part. This will be much easier to handle. You please don't think that I haven't gone to this part that fast. I have a hidden agenda behind it. Because if you learn all these things thoroughly, these are going to be very easy. Okay? So with that note, I'm going to end today's class.